Okay, so now we are going to look at the transport layer. So that's the layer above the internet layer. So the transport layer protocols are meant for end-to-end processing. Um, so we'll look at two transport layer protocols in detail, the TCP and UDP. We'll start with UDP. Now we also need to understand the difference between UDP and TCP as we go through this process. Now, what is the need for transport layer protocols? Now, the IP protocol can provide only best effort service. And the IP is mainly for forwarding a datagram from the source network to the destination network. Now, I already mentioned in the first class itself that when we talk about communication, it is between two applications running on the sending computer host and the receiving host. So it's not really a communication between two computers, it is between the applications running on these host machines. So, which means a single host could run multiple applications, same as the source side as well as the receiving host could run multiple applications. So, which means you cannot just specify I want to send from this IP address to this IP address. Once a packet reaches this particular IP address, to which application running on that destination host, the packet should be delivered. So, and then what are the expectations of receiving application? So, for example, if it's a file transfer protocol, so think about it. So, you guys would have downloaded a file from a file server. So, if you have, say, a 1 GB file, by now all the 1 GB is not going to be sent as one single packet to your receiving machine. They're going to come as multiple packets. Now we also know the packets could get fragmented on the way in at some router, or it could get lost and so on. So, but as a user, you don't really feel all these things. You just click download and you're able to download the entire file, and you're able to see the file exactly like content word by word or even by bit in the same order we expect it to see. You don't see anything out of order. So that means even though the bytes could come to your destination machine out of order, they need to be kind of buffered until the remaining bytes come. So when they are delivered to the application, to the user, they are delivered in order. So all these things have to be done. Okay. So these things are the this is a job for the transport layer protocol, especially if you need all these things to be done, we have to use TCP as a transport layer protocol. Now, UDP is also a transport layer protocol, but it won't do all this buffering and in order delivery guarantee and all these things. We'll see the differences in detail quickly. But so UDP is needed, some transport layer protocol is needed because again you cannot just deliver a message to a computer, it has to be delivered to an application. So what kind of applications can use UDP? It could be like applications that do not require such reliability, for example chatting kind of applications. So for you may be sending back and forth several chat messages, so you cannot guarantee every chat message is going to be delivered in the same order and so on. So such applications that are more kind of real time based, they are not requiring you a guaranteed service, but they are kind of time sensitive applications. For such applications you would use UDP rather than TCP. And for TCP you would use TCP for applications that require reliability in order delivery, like for example like a file transfer application or even the credit card transaction applications. So you want to pay it only once. You don't want to keep on clicking and ending up paying several times, right? So whatever you sent needs to be delivered at the destination side, and the payment needs to be done only once. So if you want to guarantee all these things, you would use TCP as a transport layer protocol. So now you see a need for an end-to-end transport layer protocol in addition to the internet protocol, because the internet protocol is mainly for routing, forwarding a message across from the source network to the destination network. Now, so that means at the destination side as well as at the sending side, you need something called a port number to keep track of the processes, the applications that to which the message needs to be delivered. And you may be wondering, can't we just use the process IDs as port numbers? I think I might have asked this question in the first module itself. So the answer is not, because we cannot use process IDs as port numbers, because each time you run a process, you might have known from your operating systems class, you might have known that the process ID could change for the same program. So you run a program and you try to find what is ID, the process ID when it is running. So each time you run the program, it may be assigned a different process ID by the operating system. So on the other hand, if you want to use something to deliver a message, the port number is like an address. Like if you are living, say, in an apartment, you have an apartment number. If you are living in a house, that's your house number. So every time any packet, any message that comes to you, it has to have the same address, right? So that's why you have something called a dedicated port number for your process. So every message that comes to the process has to have the same port number. Okay, and well-known processes, that is the reason, have a dedicated port number. So the well-known processes, for example, FTP, File Transfer Protocol, is a process. So it has 21 as the port number. Then Secure Shell, SSH, has 22. Telnet has 23. Then SMTP, Simple Mail Transfer Protocol, has 24. Domain Name Service, 53. HTTP, the web protocol, has 80 as the port number, and so on. So all the well-known processes have dedicated port number which are less than 1024. But if you're developing your own program as an application, and you want a port number assigned to it, so you need to assign it a port number greater than 1024. So that is something you need to know when you go for interviews. So you cannot assign a port number less than 1024 as a port number for your own application program. Okay, so for each process, you basically maintain a queue. It's like a mailbox. Okay, so when a packet comes to a specific port number, the operating system kind of adds it to the queue meant for the process, and whenever the process is scheduled for execution, the queue is processed, and one by one the messages are being processed. Now, one main difference also between UDP and TCP is this: UDP is kind of message based. So of course a message will have a collection of bytes, but it is stored as one message. Okay, so it is processed message by message by a process. On the other hand, in the case of TCP, it's a byte stream based protocol. So we have a buffer allocated for each process, and the process can just even read one byte from the buffer. So it could be like, of course, you are sending the whole message, but the processing resolution unit is like at a byte levels, on the byte basis. So it could just read 10 bytes from the buffer and still have some bytes to be read from the buffer. So the entire message need not be read at one go by the process. Or it could be that more than one messages could be also read in one trial by the process. So the thing that you have to know is TCP, the information is processed at the byte level, whereas at UDP it is processed at the message level. Okay. Okay, so now let us see the differences between TCP and UDP. So I have given here a sequence of series of differences. So we'll see one by one. So you need to know all of this. So UDP is connectionless and TCP is connection oriented. So what I mean by connection? So before a source and destination want to communicate using TCP, they need to able to exchange some what is called control information, and we'll see that as we proceed, in order to know the resources available at each site and set up some initial values of all the parameters that are essential to guarantee the reliable in-order communication. So what I mean by resources typically, and as I said, TCP is mainly used for like file transfer kind of applications where you will be exchanging a lot of information. So both you can, again, TCP is kind of duplex in the sense that you could, that's the next difference actually. So once you establish a connection, you can send information in both directions. So it's not like one side will always be the source and the other side will always be the destination. The roles could change, or it could be in both ways. So both side they can keep sending to the other side, and the other side could just keep receiving as well as sending. So if you want to send information from the source, say you want to send a file, a 1 or 10 gigabyte or huge file to the destination, you cannot just keep sending to the destination, because you saw already that at the receiver side things are stored in a buffer, and the receiving process has to read bytes from the buffer. So there are several processes running at each computer. So you cannot allocate the entire memory for the particular process. So only part of the memory is allocated as the buffer space for a particular process. So you do not want to do what is called overflow the receiver. That means you cannot put all your 10 gigabyte or send everything in one go and kind of overflow the memory or the buffer available at the receiver side. So you kind of communicate beforehand, before you start sending actual data, you communicate with the receiver how much buffer space is going to be allocated. So later we'll see that's called the advertised window field. So as part of the TCP header, there's going to be that field that will make the destination be able to tell the source, this is how much I'm going to allocate as the buffer space. So you have to send only this much amount of bytes as part of what's called the window. So once the buffer is cleared, the destination can again notify the source, this is my advertised window now, and the source can then send some more bytes and so on. So in order to agree on this advertised window field, the buffer space, they have to exchange some control information before sending actual data. So all these things are part of what is called this connection establishment process between the source and destination. So when you use TCP, all these things have to be done. Whereas when you use UDP, you don't need to do all these things. It's like almost like IP. You can just go ahead and send a message if you want to send a message. And the reason why we do that is it's also part of a difference somewhere down. UDP is used for real-time applications. So that means you don't want to go through this connection establishment process and then send a single, say, think about chatting. You just want to send one message, a short message, how are you, or something like that. In order to send a very short message like this, you don't want to go through all this connection establishment process, getting to know about the resources available and all this stuff, and just send that small message. It's not needed. And also some applications are time sensitive, like the video streaming applications. You need to see some portion of a movie at that time. There's no point in buffering it and playing it when it comes and so on. So when the packets are delay sensitive, it means the packet doesn't have value after a certain time. There's no point in kind of going through the connection establishment process and then trying to handle byte by byte and so on. So for such applications you will use UDP, whereas you use TCP for what is called delay tolerant applications, two familiar cases, or file transfer. So you want to download the entire file without losing even a single bit. So that's a delay tolerant application. You do not mind waiting for a certain time for the entire file to get downloaded. Similarly, the credit card transaction, you do not mind waiting for the transaction to go through and you get back a confirmation message. You do not want it to be done instantaneously. In that case, that information might be lost. You may have to retransmit. You are very you don't know whether you paid twice or it just got processed once and so on. So you just click it once and you wait for the transaction to go through and wait for the confirmation to come out. So that's the delay tolerant application. So use TCP for such applications. So that means you do not really need to establish a connection for UDP, but you need a connection establishment process for TCP. Now again, so because of this, you go through a session like file transfer. You download 1,000 bytes at a time and so on. So you go through a session for the entire file to be downloaded. So TCP is typically session based, and it's also full duplex in the sense that, as I said, it's not really source destination. The roles can change, or at the same time, a machine can take up both the roles. It could be sending as well as be receiving messages and so on. Whereas UDP is typically unidirectional. So you don't really specify what is the source and destination. Just send a message, it goes to the other side. So that becomes the source. One sending entity becomes the source, the other side is the destination. The other side wants to send back a message, it just goes ahead and sends. So it's not like you need to establish a connection and say this is going to be the source parameters and so on, and destination parameters and so on. So it's just one direction without any session. And you already saw UDP is message based and TCP is byte string based. So later we'll look at what is the maximum message size that we can send as part of a TCP. So even though it's byte based, you cannot send 1 byte at a time across the internet. So you have to send as a collection of bytes. But how it is processed at the two end host, it's at the byte level. So don't think like you will be sending byte by byte in the internet. So you don't want to put 1 byte as part of the payload for an IP datagram. So you're still going to send one group of bytes. And you already know one terminology called MTU. So MTU is the maximum size of a datagram. So similarly, there's something called MSS, maximum segment size. Okay. But one thing that you should know is the message boundaries or preserved and not preserved. So I have a figure somewhere here, let me check. Okay, so this is what I mean by message boundaries. So in the case of TCP, the sending application may send a collection of bytes like this. So this is say some 1,000 bytes, this is some 300 bytes, this is say some 500 bytes and so on. So they are all sent as what is called segments. Now they are all buffered. So now the receiving application can read information from the buffer at the byte level. So that means it could read every 200 bytes whenever the operating system schedules a receiving application to read the receiving process to read information from the buffer. It may read say every 200 bytes from the buffer. So that means the information is not read in the same size. That's called the message boundary. So if you're sending say 3 messages like this of different sizes or the same size here, they are not going to be read at the same size at the receiving side at a time. So the message boundaries are not preferred or not preserved in TCP. That is, in the case of UDP, the message boundaries are preserved. So whatever you are sending are going to be read in the same size. So because it's handled at the byte message level in the UDP case, whereas in TCP it's handled at the byte level. So that's what I mean by saying the message boundaries are preserved and not preserved in UDP and TCP. Okay. So UDP, the message boundaries are preserved because they are processed at the message level. Now because of this, actually there is issue with fragmentation. So when you saw fragmentation, right, so I mentioned that if you use TCP, there's no need for fragmentation because you know that you cannot send beyond an MTU in the source network, and you handle things at the byte level. So you will specify the segment size can be something that can fit within an MTU. But in the case of UDP, if you use UDP as a transport layer protocol, you may want your application to send some messages of specific size. So if your application wants to send a message whose size is greater than the MTU of the source network, then you may have to do fragmentation of the message with the source network itself. Okay. So of course, as I said, you use UDP for small messages like chatting messages and so on. But in case you use UDP for applications that can send long messages, then you may end up doing fragmentation in the source network itself. Okay, so that's one thing that you have to know. So if you use UDP, it is possible that packet could get fragmented in the source network itself, whereas in TCP, that situation will not arise, because you can always limit how many bytes you're going to put together as a segment and send within the MTU. Okay. Now, so we already saw this. So TCP provides reliable in-order delivery because the bytes are not going to be delivered to the application until they come in order. So if you send 1000 bytes from the sending side, and say the first 500 bytes have arrived, the last 300 bytes have arrived, but in between the 200 bytes have not arrived, the destination application is going to read only the bytes that have arrived in order. It's not going to read every byte that have arrived. So think about like a file downloading application. So when you are going to open the file, you want to see the file again, like top to bottom, that you expect to see. You don't want to see the top portion of the file, then the bottom portion of the file, and still the middle portion is missing. You don't want to see something like that. So in order to provide reliable in-order delivery, then you have to do all this buffering. Whereas UDP is best effort service. So think about the streaming application, the video streaming application. So when you're looking at a video on YouTube, you may see some small kind of disturbances in between. So that portion of the video may not have been downloaded. So the streaming application at the receiving side just keeps moving and plays the contents that it has received after that particular portion of video that was supposed to be received. So it just keeps playing whatever it receives. It buffers for a little bit, but not like forever. So it just keeps playing after whatever it receives. So that's why UDP is best effort service based, as TCP is will provide you reliable in-order delivery. So again, that's the reason you prefer UDP for real-time applications and TCP for delay tolerant applications. Okay. Now, so you use UDP for short duration communication, in the sense that because if you use TCP, you have to go through a connection establishment process. And then you spend time for connection establishment, and so since if you already spent some time for connection establishment, then you can go use that connection for communications that will be lengthy or communications that will be critical. You don't want to lose even a single message as part of the communication. So for such cases, use TCP. Whereas, as I said, if you want to just send a message, you don't want to spend time establishing a connection and then just send a message. So if you use short duration communication, then you go for UDP. Now another thing that you should really know is TCP is used only for unicast, whereas UDP could be used for unicast, multicast, or broadcast. Now if you think about it, why TCP can be used only for unicast? Because TCP is designed to provide reliable in-order delivery guaranteed service. And think about a multicast problem. So multicast means one sender is trying to send a message or send some sequence of messages to multiple receivers. So one receiver might have received, and if some other receiver might not have received a message, then if you use TCP, reliable in-order delivery, you have to retransmit the message. And think about multicasting, it's not multiple unicasting, you still send only once, like you saw the multicast tree. So you send the packet goes across all the routers in the tree. So it is sent only once. So if you want to retransmit, it is like sending the same message again. So it means one entity that has received the message will again receive a duplicate copy of the message. The other entity which has not received will just get it for the first time, but some may get it more than once. So you don't want such things to happen. So that's why you don't use TCP for multicasting. And the same thing with broadcast. You don't want to keep broadcasting the same message again and again until everyone receives it. So a broadcast or even multicast can be only best effort service based. If some receivers don't receive that particular message, then they don't receive it. So you use UDP, it provides only best effort service. So that's something important to know. So you use UDP for all types, unicast, multicast, or broadcast, whereas you use TCP only for unicast communication. And we talked about fragmentation, that in the case of TCP, you don't require fragmentation in the source network because it's done at the byte level, whereas UDP, you may have to fragment at the source network. If the application you're using for UDP would like to send a very large message. Alright, so with that we finish the difference between UDP and TCP. So let me stop for a minute.